Hello, my name is Bobby Hilster and I am your particle model guru. Today's video is about redshift and tired light and a couple of other ideas about the expanding universe. If you're new to the TPM, I suggest you watch the particle model overview, levels of the universe. And in addition, I recently released a video describing EM radiation in general and how the particle model, how I came about the idea of a stream of particles for light. Interesting video. Recently, my son David, interviewed a Dr. Unsecker from Germany, and Dr. Unsecker wrote a book titled Einstein's Missing Key. He reports that in some of Einstein's work, he discusses the idea that the speed of light varies, but just how it might vary was not clear. But in the same context, Dr. Unsecker mentioned tired light, and I thought about this before, but concluded that tired light did not explain redshift. But the interview got me thinking about all of this, and hence this video. So let's look at the definition of redshift from Wikipedia. In physics, redshift is a phenomenon where electromagnetic radiation, such as visible light, from an object undergoes an increase in wavelength. Now, blue light has a shorter wavelength than red. And here's how you get this in general. Let's assume that this is green, the wavelength of green, and that's right in the middle between blue and red. So if green shifts, if the wavelength gets bigger, it's shifting towards red. If green's wavelength gets smaller, it's shifting towards blue. So it doesn't matter what the frequency is, it matters in which direction the wavelength is going. A longer wavelength is called redshift. Okay, well, one of the things that intrigues me is how you measure wavelength. In the first place, how do they know? And this is a schematic diagram, a very simplified version of a schematic diagram for an EMF detector. It's written down here in the link. And what you have is a 1 millihenry inductor and a 100 nanofarad capacitor, which is tuned to a given frequency. And as it receives that signal, the op-amp amplifies it enough so that it can be detected, and you can read the value of the intensity of that wavelength using the meter. You apparently can also listen to it. Simple diagram, but at least it makes the point. Now, if you were to put a scope on this to measure it, and I can tell you I put a scope on some circuitry many times in 40 years of working on circuits, I know this is what you're going to see on a scope. You're going to see amplitude, the peak, positive peak, and the negative peak, and you're going to see it over time. It's going to display the amplitude over time, taking recordings and displaying it on the screen. So what you're measuring is amplitude in time, but what you want is wavelength. Well, in order to get it, you have to assume a value for speed. And of course, what other value would mainstream science pick? Sure, C as the value. And to calculate the wavelength, all you need to do is multiply C times the time interval between peaks. That tells you the wavelength in meters per one cycle if you take the time between this peak and that peak. So that's how you get wavelength. You can't measure it. You have to measure amplitude and time. Interesting point about our eyes. We don't detect red shift per se, but we detect light, and it's based on the arrival time of the peaks. Our eyes can't measure the speed of light as it enters. It can't measure the wavelength, the distance between the peaks as it hits our eye, and it doesn't measure the frequency. What it does, and it's very simply put, is that if this is the cone, this point here, my thumb is the cone, and light hits that cone, as long as it hits it in synchronism with the cone of that cone, I contend, has a resonant frequency, just like the LC circuit I just showed you. It measures the arrival time, not the wavelength, the arrival time of the peaks. Just an interesting side point. So the redshift, they claim, then says the Earth is not the Earth, the universe is expanding. And to do that, they have to make some assumptions. It is assumed that the distant star emits light with the same spectral pattern as a nearby star. So they measure a nearby star and they have something to compare to. It is assumed that the speed of light is constant, namely and specifically c. If the star is not moving, it should give the same spectral pattern because nothing else should happen to light as it moves through open space, and hence no redshift or blue shift. If the star is moving away, the wavelength should increase, and that's because as it releases one peak, and the peak starts moving, and if the source is moving away, I don't have it. If the source is moving away as the peak is moving away, the wavelength gets bigger. Okay, if the star is moving the wavelength, and hence you have a frequency shift towards red. And this, of course, is just like the Doppler effect that you hear from a siren on an ambulance going by or a police car going by. And it's higher as it comes at you, and it fades way lower as it goes away. Same principle. But you have to make all these assumptions to come to that conclusion. Okay, that brings me to tired light. This tired light concept was first proposed in 1929 by Fred Zwicky, who suggested that if photons lost energy over time through collisions with other particles in a regular way, the more distant objects would appear redder than more nearby ones. Well, there's no... that's all you get. It's lower energy through collisions, light, photons hitting other objects. Why it loses energy, I don't know. Why there's a redshift, it's not clear. Well, I bring up my own answer, and whether this is Planck's equation here, it's really applicable to emitted light from an object, and it seems to come out in quantized values. And this is a quantized equation, although it doesn't show it. But the energy, Planck concluded energy would be equal to his constant times the frequency. So if you really like equations, you could say, well, when the energy is reduced, and Planck's constant is a constant, then the frequency is reduced. A reduced frequency, a smaller frequency, high frequencies have a small wavelength, low frequencies have a large one. So if you reduce the frequency, the wavelength gets bigger, you have redshift. Well, I'm not a fan of using equations that apply to one thing and then make it apply to something else, but at least that's something. Redshift, but this is all about redshift happening during transit. It isn't about what the source is. It isn't about whether the source is moving. It's about what's happening while it's moving through space. Okay, a third point. David also reviewed a book by Halton Arp. The book is titled seeing red. And he states that there is a galaxy that has two quasars attached. The detected electromagnetic spectrum that shows that the two quasars have a different redshift than the attached galaxy. In other words, these three objects are very close to each other. In fact, you can even visibly see how they're attached, and yet they have a different value coming from them. He said, well, shoot, if they're that close, even if they're moving, they should have the same redshift. They don't. They have a different redshift, which means that maybe there's what he calls an intrinsic redshift. That is, objects do, in fact, emit different frequencies and give you a different spectral display from those stars. So he's saying you got to know what it is when it's being emitted, even if the object is stationary. So that was his explanation. He said no redshift. Well, what does the particle model say about all this? And this is the particle model for light. I've talked about this many times. Individual particles moving at or about speed c. And the peaks are determined by the fact that there's more particles here, and there's very few particles in the valley. There are two things that can happen to light as it moves through space. This addresses the transit issue. The G1 particle field, which is all around the G1 light, hitting it from all directions, can hit the G1 stream and scatter the individual particles. It's going to knock them away. In that case, well, I'll cover that in a moment. The G2 particle field will cause the speed to slow down due to drag. Let me go into that then in a little more detail. The intensity of the G1 particle stream is primarily in the number of G1s at the peak. That's what it's really all about. When the G1 particle in the G1 particle field hits one of the G1s in the stream, the intensity, or possibly the energy of the stream, is reduced. That is a way for light, in the case of tired light, for the light to hit something and lose energy. And reduce its intensity. I call it intensity, but it could be considered energy. But in this case, the wavelength doesn't change. So it isn't following Planck's constant at all. I mean, you can't, in the case of the particle model, it would say Planck's equation does not apply because you can get a reduction in intensity this way, but you don't get a change in wavelength. No redshift, no blue shift. G2 drag is caused by the G2 particle field, and it's the sustaining force of the G1 particle stream. It's the force that keeps it moving in the same direction and at the same speed, whatever the speed is. And it's hitting this stream in all directions. Drag is caused by the fact that head-on collisions, that is G2 particles coming this way, hitting against the oncoming G1 stream, is stronger than G2 particles coming this way. Very slight bit of drag caused by the speed difference between the G2 particle, which is very, very fast, and the G1 particle, which is only going at the speed of light. But if that happens as it goes through this field and it experiences drag, all the G1 particles in the stream slow down. They're all going to slow down nominally at the same rate. So the speed is less. But again, the wavelength isn't going to change. But the speed is less. Okay, so they all slow down. When all of the G1s slow down, yes, the TPM suggested that the speed of light slows down as it moves through space. There is no change in wavelength. Now here's a different equation, pretty much a basic equation, which normally you see as C equals F frequency times wavelength, lambda. I replace it with S because if I said C, you would interpret that as a constant, and I'm not saying the speed of light is constant. So this is the speed of light as it transits from a distant star to us, and its value is the product of the frequency type wavelength. So I'm going to rewrite this equation. I'm going to change frequency to cycles per time, and then rearrange and solve for, to bring this on the other side and bring S to this side, and you get time. The time for each cycle is equal to the wavelength times the speed of the light. This is the speed of the G1 particles. So as the speed decreases, you have this value drop, goes down. Wavelength is the same because it doesn't change from the G1 particle field or the G2 particle field. You make this lower, and this is a constant, this is higher. So the time per cycle is larger. Not the wavelength, the time per cycle is larger. As the speed decreases and the wavelength stays the same, the arrival time of the peaks increase. And that is what our eyes detect, and I claim that this is what you are able to actually measure. If you use a meter, you're measuring the arrival time. And you can measure the amplitude, of course. But one of the key aspects that's not mentioned anywhere is, what is your model of the universe? What does it look like? I mean, how can you say all these things and make say, okay, the universe is expanding, and you don't tell us what the universe looks like? Okay, well, one model could be this. Space is infinite, or infinite open space in all directions, but matter is contained in a finite sphere. Okay, so space is infinite, but all the matter in the universe is contained in this sphere. The particle model would indicate that since the G1 particle source and the G2 particle source are all inside the sphere, that there would be a net force on the objects at the edge of this finite universe, finite set of matter. They would move away. If that's your model, it would move away. So that's, I'm not going to go in a lot of detail on that, but let's talk about a different model where space and matter are both infinite. So wherever you go in the universe now, you are in the center. It's ironic. You can go an infinite distance to the left and you're still in the center because there's still an infinite more to the left. So you are always in the center, and therefore the G1 and G2 force fields are balanced in all directions. And the particle model would indicate that the universe then is neither expanding nor contracting, because there's a balanced set of forces. When the space is finite, infinite, but the matter is contained in the finite area, it's not balanced at the edge. There's a net force outwards. But here, in the infinite space and infinite amount of matter, no matter where you are, it's always balanced. So, well, and maybe you can define other models of the universe, apply whatever theories you want to apply, make whatever assumptions you want to make, come up with whatever answer you want, which is about what it happens. Okay. Okay, the question is, what are your assumptions? Is the speed of light constant, or can it change? Do all stars emit the same EM spectrum, or can they emit something different? Does the loss of energy cause redshift? What is your model of the universe? You make your assumptions. You can choose. You can, with all these variables, come up with any answer you want. Well, let's do something. Let's do kind of a thought experiment. We're going to prove all this out. Okay, so let's do a real measurement. Let's go to a star that's 100 million light years away and measure the spectrum. Okay, we measure it and we send that back to Earth, and then 100 million years later, when the Earth receives that same spectrum from that same star, they can measure what it's received and compare. Kind of an impossible situation, clearly. And what about the speed of light? Even though you go out there and measure it at later at the Earth, what about the speed of light? What do you say about it? It's tough. You can't easily measure that. But here's an interesting point. Would our sun, looking back the other way, would it be moving away? If we went all the way out there and measured all the redshifts from all the stars from this whole totally different place, would there be redshift on all of the objects? I guess we'll never know. Interesting thought, but it brings up a kind of paradox. Okay, my name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.